Good evening to one and all present here. Thank you for your presence and for spending your precious time to attend the session, which is awaiting you to give the knowledge which you wouldn't mind to take back to yourself. Now let's start the session.
Hey Shabana, are you familiar with the IEEE St. Joseph College of Engineering student branch?
Yes, Ritika, I'm quite ac- acquainted with them. I follow their activities closely on social media and they consistently host intriguing events. Today they are conducting a session called Erudite Session 9.
Wow, that's interesting. By the way, what does erudite mean?
Well, erudite refers to someone who is highly educated, cultured, and knowledgeable across various subjects. In this context, implies that the speaker for today's session is exceptionally well versed and sophisticated in their expertise.
That's so enlightening. So, what's on the agenda for today's session?
It's part of the Season 9 series, an international webinar series that has already seen 8 successful sessions. They bring together keynote speakers from around the world to share insights and expertise.
That sounds like a fantastic initiative. Who's the speaker for today's session?
Today's speaker is Mr. Fidel Makatia, is an exceptional individual with a remarkable track record in engineering and innovation. His notable achievements including spearheading the development of Africa's first locally designed ventilator, the Tiba vent in response to the COVID-19 pandemic, and also earned Fidel recognition as the United Nations Person of the Year in 2020.
Alright, let's join the session.
I welcome you all to the exciting webinar event hosted by IEEE Student Branch Chapter of St. Joseph College of Engineering, ERUDITE'24, an international webinar series Season 9.
Now, let's start with our speaker's welcome note. Ladies and gentlemen, it's our pleasure to welcome our distinguished speaker for today's session, Mr. Fidel Makatia. Sir, an exceptional individual with a remarkable track record in engineering and innovation. As an electrical engineer, he has demonstrated a strong commitment to using technology for societal transformation. His notable achievements include the development of Africa's first local design ventilator, TIBA vent, in response to the COVID-19 pandemic. This groundbreaking innovation not only showcased Kenya's innovation capabilities but also earned his recognition as the United Nations Person of the Year in 2020. In addition to this contribution to healthcare innovation, he had been actively involved in various projects aimed at advancing technology and addressing societal changes. He has served as a team leader for initiatives such as Cook Hub Nano-Satellite Project, which aimed to revolutionize agriculture practices in Kenya through the use of Geographical Information System (GIS) and UAV guidance. His dedication and innovation and volunteerism had been further acknowledged through prestigious awards, including the Head of State Commendation from the President of Kenya, H.E. Huru Kenyatta, and Larry K. Wilson Regional Student Volunteer Award from the Institute of Electrical and Electronics Engineering IEEE. With his passion for engineering and his commitment to making a positive impact on society, Fidel Makatia continues to inspire others and drives a meaningful change through his work. Please join me in the welcoming him as he shares his insight and experience with us. Thank you for accepting our invitation, sir. Now the session is entirely yours, sir.
Wow, thank you so much. That was very was a lot. I was wondering, is that really me? I'm really honored to be here. Hope you can hear me. Let me share my screen. Um, Sorry, most of these slides I just finished presenting from one of the branch. can you see my screen? Just
Yes, sir.
confirm it.
It's visible.
Okay, that's fine. So I can introduce myself. You guys have done a very good job. So one thing I'll introduce, however, is I will encourage all of us to join the ARM Developer Network. It's free. Here you get to interact with ARM engineers, ARM experts, guys that have been developing with ARM technologies all over the world. You will get to join the Discord channel for free, whereby you can extend and improve your embedded development skills, SoC development skills, all kinds of developing on ARM, Windows on ARM, ARM on laptops, desktops, and stuff. So this is the QR. Just scan or use the link. I will copy it in the chat. Scan, join. They will only ask you for your corporate email, so student email or work email. Just say you're a student. Then also, once you join, Arm will send you swag. So make sure you put the right address there. So I've had people that Arm have personally sent very cool swags, including t-shirts, bags, cape. So it's a good thing for students and early professional guys to join. So I'll encourage us to join. I'm also part of the program. I've interacted with very powerful ARM engineers that design ARM architecture, and you can ask them a lot of questions and they will help you. They're also cool people in the community that are really ready to help in your learning process. So you don't have to be experienced in ARM. If you're a newbie, join. If you're experienced, join. It's for everybody. So I'm saying this because it's very important. It has really helped me at least improve my ARM skills. Okay, let's start. I don't have to, based on judging from the introduction, I know you guys have been introduced a lot to microcontrollers, but I'll just briefly speak about it. So there's the world of embedded systems, which does not necessarily mean microcontrollers, but most of us are used to microcontrollers. Today, my main focus will be system on chip design. So I will just but briefly talk about popular architectures on system on chip. You're either 8-bit, 16-bit, or 32-bit. So nowadays, the world runs, we are in a smart and intelligent world. So almost everything is automated, from agriculture to even how we wash our dishes to very small jobs that we didn't know can be automated are nowadays automated, thanks to improvement and development in the area of IC and microcontrollers and microprocessor system on chip. And nowadays, system on chip, microcontrollers and processors are cheaper compared to last 10 years. And this means that almost everybody can actually include them in their workflow and automate most of the processes. Most popular architectures are, like I said, 8-bit, 16-bit, and 32-bit. So if you have used Arduino before, that's a good example. Arduino Uno, that's a good example of an 8-bit. 16 bits are rare, although I know PIC by Microchip, they make 16-bit systems, but they are rare. ARM merges on 32-bit systems and 64-bit systems. So 64-bit, a good example is Raspberry Pi 5. A good example of 32-bit, 64-bit is also your phone. So either you're using a Samsung phone or an iPhone, or you're using a Techno, you name it, this based on ARM. And it's that's a 64-bit. I don't think there's 32-bit phone nowadays. So 32-bit is kind of like the sweet spot for most of the embedded systems applications. So example of 32-bit microcontrollers, I'm going to show you in the next slide. We have STM, we have NXP, we have even Microchip. They are at some lineup is based on 32-bit microcontrollers. So ARM runs majority of the SoCs are produced on ARM. So there's these statistics here that 6.7 billion, and this is just 2020. So by now it has really grown because most people are adopting ARM-based architecture. Apple recently, might not be recently, but 4 years ago, shifted from Intel to ARM. So that was a very huge shift. And nowadays, Apple is very fast. I'm using Apple MacBook M1, and it's super fast compared to before then. I used to use Lenovo P1, which is Intel based. And yes, it was fast, but it was very power hungry. But the shift to M1, which is based on ARM, and the M series, M1, M2, M3, right now they're in M3. It is it was very well welcomed and really made a boom in the ARM in the laptop sector. So we know currently there are talks on Windows on ARM. So companies like Qualcomm, they're making uh, processors that are based on ARM. So very soon, everyone that uses Windows will have an option to either do Windows on Intel or Windows on ARM. So ARM architecture is really growing. So it means it will be, if you're an embedded developer or electronic engineer, computer scientist, it will be good for you or prudent for you to learn ARM architecture, because you will use it one way or the other in your work, or even in your innovation, or even in your startup, because it's on these guys that start startup that actually drive this world. I already talked about this. These are examples of 32 8-bit microcontrollers based on AVR CPU. These are example of 32-bit microcontrollers that are based on ARM. You can see ST, you can see Raspberry Pi. The Raspberry Pi 5 is only 64-bit, but 4 and below we have 32-bit and 64-bit options. You can see an XP there. Okay, let's now dive deep into a system on chip. The embedded world is divided into two major architectures, or system on chip. Even if we forget about the embedded world, one of them is the RISC architecture, which is reduced instruction set computers. Then we have complex instruction set computers. So these are two vast sections of the system on chip design. So CISC, a good example of CISC is Intel and AMD. A good example of RISC is, like I said, ARM, NVIDIA, Apple. These are RISC. So differences between the two. So CISC stands with complex instruction set computer. So it means the instruction set is complex. So it means it takes a lot, sometimes some cycles to decode the instruction set itself. So it means I'm actually trying to explain the first point, complexity of the instruction set. But reduced instruction set computers like AVR, like ARM, it's simple. So fewer clocks to decode an instruction. Like, let me get my pen. So, there's the opcode and operand. If you operand, okay, this is very slow. Next time I will have to write this. Opcode. So it should be the other way around, actually. Opcode should be here. So opcode is instruction set, operand is arguments to be executed. So this, like, you can see this as data, you can see this as instruction. So this is what I'm talking about. For RISC, it is very reduced. So very simple instructions. So it takes fewer clocks to execute. It's not, the instruction is not as powerful as a complex set CISC, but it's reduced. So it takes less time to decode, and it's also not power hungry as CISC. So execution speed depends. So depending on your application. So RISC, since the instruction set is minimal, reduced, it means it's fewer clocks to execute, so it's faster. Although there are some complex tasks that RISC will take a lot of clocks to do, then CISC, since it's complex, it might be faster. Why? Because it means one instruction can execute a lot of things at once. But it also depends, because it means you take also a lot of clocks. So traditionally, before the ARM revolution, CISC was well preferred than RISC. Why? Because CISC was based on Moore's law, whereby the more you increase the number of transistors, the more you improve the performance. And that people were really doing it. We had even people like AMD that really put a lot of 1 mega chip, a lot of cores in one chip, and it really increased the performance. Why? Because with CISC, you can really get faster speed. The more you increase the clock, the faster you get, but something else increases, which is power. And we only have, power is limited always, because your laptop cannot, this the maximum amount of power you can draw from your laptop. So the more you increase the size of your battery, the more it becomes bulky, the more it's very impractical. It turns into a desktop. So that's why people started exploring the RISC architecture, and that's where ARM comes in with the RISC architecture. Yeah, so it depends. Hardware complexity for RISC, since it's reduced instruction set, implementing the instructions is very simple compared to CISC. CISC is a bit complex to implement, although not hard in the modern world, but it's complex regardless. Memory usage, RISC better because it's reduced instructions, so fewer instructions, simpler to implement, so the memory needed is small. Like in your STM board, you find out that the RAM is very little, 4KB, let's say. But in your Intel machine, you find out the RAM is, let's say, 4GB, 16GB, 2GB. So that's the difference. Although nowadays, like in MacBook, the one I have is 32-bit GB, 32 GB of RAM. So this point is, it depends also. Energy efficient. This is very energy efficient. I remember when my MacBook was new, I used to stay even 2 days, okay, not 2 days, but 1 day and some few hours without charging it, and I would be using it without, it doesn't go off. And trust me, I do a lot of heavy lifting. But CISC, you can't stay with more than, say 4 hours or 5 hours with an Intel machine, because CISC are very power hungry. So these two depend on application, is dependent on application, all these points. Why? Because we have gaming consoles and gaming machines which are not based on RISC. Why? Because CISC can handle gaming very well. Although that is changing, because NVIDIA, which makes GPU, is based on RISC. So ARM is trying to improve so much on their architecture so that they can support even gaming, like let's say FIFA or Call of Duty or any complex game. Your PlayStation, your Xbox is actually based on CISC architecture, most of them, because CISC is preferred for such high performance and high throughput. Although, like I said, now in the modern world, there's a very fine line between those two, because there are a lot of guys doing a lot of research on these areas, and they are coming up with a lot of, every day there's a lot of development. So in your SoC design, there's a chance that you will always develop with RISC mostly. We're going to talk about that today. CISC, if you're interested, you can explore the CISC architecture, how to increase the multiple cores and stuff to improve performance. Although, if you ask me, but this is just my opinion, this architecture is slowly going away. People are shifting, because people actually said Moore's law has died, has ended. So people are really shifting toward RISC, and of course neuromorphic computing and other kind of computing paradigms. So we are slowly moving away from CISC. Okay, that's a story for another day. So, okay, focusing on RISC only, I saw this article by STM where they tested a microcontroller or system on chip that can last for 15 years on battery, single charge. This was a groundbreaking performance. So it means you can actually achieve very low power with a CISC architecture, RISC architecture rather. And I saw it. It's good for me to show you. I use this a link here, so when I share the slides, you can click the link and read about it, what they did. So this is very promising in the RISC field. So what's, just briefly also, what's the difference between 8-bit and 32-bit? Why do people prefer 32-bit ARM cores? Okay, for starters, it's high processing power. So you can clock even 400 megahertz with a 32-bit MCU. So that means you can drive high quality graphics. You can do a lot of tasks, high performance. Of course, it also means you consume more power, but it means you can drive powerful applications, like you can run DSP algorithms on it. Why? Because it's faster, so to speak. The bus size is bigger. Why? Is 32-bit. So it means you can handle more data and more complex algorithm. People are actually working on what we call TinyML, where machine learning algorithms are being deployed on SoCs. Why? Because it's possible now to have complex, we have a lot of databases and bits to manipulate. Most of ARM MCUs ship with a DSP, digital signal processing cores or processors, and floating point units. These are very helpful, especially if you've done ML nowadays. Floating point, we call them flops, but in microcontroller language or SoC language is FPUs. But in ML or AI language is called flops. So flops really matter. Precision in LLMs, let's say like ChatGPT, really determine their performance and accuracy. So with this kind of hardware, which I'm gonna show you how it's integrated, it's very possible to have very powerful programs that are running on 32-bit systems. So traditionally, guys, 8-bit you cannot run, doesn't come with these two. So you have to do your processing elsewhere, dedicated ASIC for just signal processing. Then you now move it to your main core. But nowadays you can actually do it in the core, because 32-bit support these two. You can connect more advanced peripherals on a 32-bit system. For example, a car communication system is using what we call a CAN bus. You can't connect the CAN controller on an 8-bit, but the 2-bit can support CAN, can support even complex peripherals, that are not supported. There's something called an NVIC, nested vector interrupt controller. We talk about it in a few, so I won't dive deep, but you can have a lot of multitasking on a 32-bit than 68-bit. There's what we call RTOS, real-time operating system, that can run on 32-bit. Well, some people have tried to run it on an 8-bit, but the performance is not comparable to a 32-bit system. Scalability. So 32-bit means that you can actually code that 8-bit application on a 32-bit system. So it means that if you change your mind, you don't need to add a core or remove a core. So what you need to do, you just reprogram the same system. So it's very scalable. Every time your IoT application is robust, meaning you can always add new segments to it. You don't need to add hardware necessarily because the hardware is embedded. So it's easy for you and your clients or your innovation. Should you change your mind, should you add a feature, you just change your code. You don't change any other thing. So that's good. Okay, and maybe a sensor or two. Power efficiency, I just talked about this. So traditionally, guys used to say 8-bit is more power efficient than 32-bit. But nowadays, with the advancement in ARM architecture, there's a very fine line. Like I showed you, ST is achieving 15 years battery life. This is simulated, of course, not tested on ground. And this, I don't think there's any 8-bit that has recorded this kind of simulated results. So it means that nowadays you cannot buy a 32-bit, 8-bit saying it's more power efficient, because there are guys that are achieving 32-bit power efficiency that are higher than 8-bit. Cost also. So cost nowadays, the cost between, because traditionally guys were saying that 2-bit is more expensive than 8-bit, but nowadays has made it so affordable until they are very comparable. So my point is, if you can do 32-bit, why not? Why go for 8 and you can actually do 32, and they offer the same advantages and even more. So, but it depends on you. So ARM architecture is divided into 3 major categories, or ARM boards. We have the Cortex-A, which is highly performance-oriented applications like car infotainment system, like Wi-Fi routers, like, home management systems. So all these are based on Cortex-A. So if you let's say drive in a Tesla or in a Mercedes-Benz or any car that has an infotainment system that shows a map, uh, chances are you're actually using a Cortex-A there. A good example is actually your phone. Any smartphone is based on Cortex-A, so it's mostly optimized for performance and not power. So that's why, because they assume that you will always be connected to power, so you have a chance to charge it. So like your phone, they know that in the evening you will charge it. The car is obviously connected to power always. The router is always powered, so they don't care about power, don't care in quotes about power efficiency. Why? Because um, they optimize performance, so you can drive the best graphic, drive the best speed. So that is Cortex A. There's Cortex R for fast response. R is for real time, hard real time systems. For example, in embedded system for satellites application, once you launch it, you don't want it to fail, because you don't have a chance to go and remove the satellite from space and fix it. So once it's launched, it's launched. You can't do anything. So you need a microcontroller or an SoC that is best built on real-time applications. Um, we don't use hard disk nowadays. A good example would be hard disks or data controllers, that once it fails, you lose all your data. So you don't have a chance for recovery. So this is mostly for that, or robotic systems that are in high profile places, like let's say nuclear power plants, or medical systems. They use Cortex R, because you can define recovery area, whereby if everything fails, where should be the default location for your, default code for your MCU or your SoC. So it's built for that. So we have Cortex M. M is for embedded. So most of us, we actually use Cortex M. Most microcontrollers that run almost everything, IoTs, our headphones, our smartwatches, you based on Cortex M. So there's a chance that if you build an SoC, you're going to use a Cortex M. You can use Cortex A, you can use Cortex R, but most of the applications is actually Cortex M. So if you know this, you know how to choose which architecture to use. Okay, architecture is the wrong term, as you'll see in a few, but which category to use. Yeah. I profiled some Cortex M cores. This is M7. This is, we are gonna dig deep into all these peripherals. I'm not sure time will allow us, but we'll see how much we can cover. Let me put my watch here so that I don't speak until my evening. Okay, you can see there's M0, there's M3. Now this is M0 plus. It used to be M0. There's M3, there's M4, M7, there's M33, M20. So we're the naming convention is usually, if you see M7 or M30 something or M20 something, it's very either high performance. Like okay, let me not get ahead of myself. We'll get there. But you can see, for example, if you pick this M7, you can see the CPU is here, and this is the version 7. So M7 is usually, if you see M7, M4, M0, there used to be an M1, but I think they canceled it. So there's M3. So that means it's version 7 or and below. If you see something like M23, it's usually version 8 or version 9. So as you can see, the components, we are going to go through these components one by one, what they do. But the CPU is based on ARM. But the other things, for example, the cache memory, instruction cache and data cache, the TCM, tightly coupled memory for data and instruction, the AXI and AHP, that's part of the AMBER protocol. You're going to learn in a few, just in a nutshell. There's the WIC, there's the NVIC we talked about, nested vector interrupt controller, DSP, there's FPU, there's watchdogs, this for your debugging, JTAG and serial wire, for your error correction, for memory protection. So all these are not, the core is actually this one, CPU, but it comes with all this so that your application, so when you're building your SoC, can connect to all this. So M4 is also having all those things except a few. So M4 and M7, they are almost the same base, but the difference is M7 is usually twice processing speed than M4. M0 is usually optimized for low power consumption. So if you're looking for low power, the WIC for M0 is very efficient for that. So you can put your controllers on, let's say, sleep mode or deep sleep mode. So let's say you're building an application, an agricultural application, you just want to get notified when something happened, an event happened. So you don't want every time to get information of temperature and let's say humidity. So you put your controller or your SoC on deep sleep mode. So it shuts down most of the clock, because power in a microcontroller is dependent, directly proportional to the clock. So this is how you calculate digital power. Okay, it's FC V squared. So something like this. I might have forgotten the formula, but it has frequency unit. You can do very little with voltage because voltage is fixed. Nowadays is 1 volts and below. So let's say 1 volt is the maximum voltage your SoC takes. You can actually use 0.6 volt. That's the least required to generate your clocks. So, but you see this frequency here. C is the capacitance, which you might not do anything about it. Maybe you can reduce the capacitance when you're doing design by reducing the size of your transistors, which you can talk about maybe in another series. But now there's frequency. So it means that the higher the frequency, the higher the power. So basically, if you can switch off most of these clocks, you can optimize your power use. That's what M0 does the best, used mostly for such kind of applications. Okay, I think we can now talk about the ARM architecture, then we can get back here. So one interesting fact about ARM doesn't make any chip. So it doesn't do any any IC fabrication like TSMC or NVIDIA. So what they do, they create the IPs, intellectual property, and they license it. So once they create, let's say M0, what they do, they will license it to vendors like STM, Apple, NVIDIA will now use the ARM architecture to make their own chips. So they don't make chips as such. So these are some of the IPs that ARM makes. Apart from CPUs, they make GPUs like Mali. They make interconnects. We'll talk about interconnects when you do SoC design. They make system controllers, peripherals, UART. I know you guys have used UART and SPI before, so they make such controllers. They make all this. So they don't, okay, they design all this and license it. So it is their IPs. But now when you want to implement this, let's say this kind of UART peripheral in your system, so you will license the IP from them and implement it. So you don't buy a chip from them, no. You license an IP from them and use it. So they're in the licensing business, so to speak. You can access this whole list also from the link below. So I look at ARM architecture's evolution, starting from version 4. Now we're in version 9. Most of us use version 7 because it works. We have not seen any issues. So most applications are in version 7. But there's version 8. So as you can see, there's improvement in some aspects. So I want also to say it's backward compatible. So version 9 will support everything else. Version 8 supported. Version 8 will support everything. Version 7 supported. Version 7 and so on, so on, so on until the first version 4. One of the key improvement in version 9 is machine learning, additional signal processing, and security. So machine learning is because the world nowadays we're in the AI revolution. We also want to put AI on SoCs, not just on data centers. So that's why version 9 is optimized for such. Version 8 is optimized for all these things, which version 9 supports. Version 7, all these other things. Version 8 supports version 7, like I said, and so on. So right now we're in ARM v9, which is very powerful and very energy efficient. But like I said, most of your application might actually be in version 7. So one of the advantages of joining the ARM developer program, also you can apply to get some access to some of the version 7 IPs like M0 IP and implement it in your FPGA, which is something we can talk about when we get time. How do you do that? And when you want to test, let's say your SoC, you can burn it on your let's say M0 core, burn it on your FPGA, and use it to test your SoC before you design the chip itself and get it fabricated. If that's what you want to do. If you're not designing the chip, you want just to create an embedded system application, what you do, you just buy a already designed chip, like let's say an STF4, STM32F4 chip. You create a PCB for it, use it for your application. But now you decide which version of the chip you will get, or which category. Is it an M0? Is it an M4? And such. Okay, let's talk about the architecture. So like you see, all this architecture has changed over the years, but there are some things that remain constant, the core of the architecture. Let's talk about that just to get you guys started. Then the others you can obviously read from the internet or online or through the ambassador program, their trainings on how to do the same. So the key concept is the one I'm talking about. They don't change much. So what is the difference between architecture and microarchitecture? It's very simple per se. Architecture is like the blueprint, instructions. This is how things are supposed to be done. This is how things are supposed to be implemented. This is how registers look like. This is how the buses look like. But microarchitecture basically is how do you implement the architecture? So kind of like the architect drawing the building, giving the civil engineer the drawing of the building, the blueprint. Then the civil engineer now implementing the drawing in his own way. So that's the difference. So ARM develops the architecture, yeah, just to stress. So we'll talk also concept of thumb and thumb2 instruction set. So one of the key things about RISC consists, remember I said, if you remember, still remember, I said RISC is reduced instruction set. So it's very power efficient, but it's not as powerful as CISC. CISC is complex, power hungry, but very powerful instruction. So the thumb instruction and the thumb2 instruction. So as you can see here, thumb is 16-bit instructions. So it's more of a RISC instruction. So it's energy efficient, but is not as powerful as a CISC. So what ARM did over the years, they created what we call thumb2 instruction sets, which what they do, they combine both 32-bit. So these 32-bit instructions that are so a good example of an instruction is like load, store, add, multiply, those are instructions. So what they did, they created thumb2, which combines 32-bit and 16-bit instructions. So most of the instructions are 16-bit for energy efficiency, but very powerful 32-bit instructions are retained to make sure that the efficiency and the performance of the chip is high. So when you're burning an ARM SoC you're burning an ARM core in your SoC, you have the option to use both of these. So where you need efficiency, you use that a 2-bit instruction. Where you need power, this is performance rather, you use the 2-bit instruction. Where you need power efficiency, you apply 16-bit instructions. So that's what makes the ARM architecture very powerful. You have all the combination of both high performance and low power instruction. Use it when you need it. Most of the performance instructions are 32-bit, like DSPs and stuff. But for power efficiency, they're 16-bit. So yeah, so the ARMV, this is for ARMv9. I only got this diagram. You see it's in between where you have both 32 and 64. And it started with V7, so V8 also does the same, and V9 does the same. We'll talk about AMBER concept, advanced microcontroller bus architecture, which is a very powerful thing. Pipelining, which we know, we're going to talk about in the next slide. DMA and NVIC is a very powerful feature of the ARM core also, which is very efficient. We'll talk about in a few. Peripherals, these ones, you know, SPI by Philips. There's I2C by Philips, SPI by Motorola, or the other way around. UART, USART, ADC, UART and USART are the same thing actually. This should be I2C. So ADCs and such. Then there are clocks. So your SoC should have all this. So usually from the previous diagram, but I can still draw it here. Usually this is your SoC. Then this is your ARM core. So usually you have ARM. Then you have other IPs here. IP stands for intellectual property. You can call it blocks. Let's say you have your ADC here. You have your SPI control driver here. You have your LCD, let's say LCD display driver. You have your, let me say, power management unit, PMU. So all these are connected to your ARM core. So this is one chip or IC. It can be, let's say, even 1 centimeter by it can actually be smaller. I've designed chips that are even 1 millimeter, and this is plus packaging. So they can be smaller than this, depending on the technology you're using. TSMC nowadays, they're saying they're working on 2 nanometers. So this means chips can actually be very small and more integrations can be put in. So how do you communicate with all this? That's where AMBER comes in. How you communicate with the peripherals. ARM gives you this, so you don't have to design this yourself. ARM will give you this. Then you can get this from another, let's say from NXP, another vendor. You can get this from power management unit, let's say Texas Instruments. They're very good in that. You can get this, let's say from ADC, from let's say Saris Logic or Marvell. Your ADC IP and stuff. Then you connect all this. You can use programs like Synopsys or Cadence, design all this in one chip and connect them. Then you can send it to TSMC for them to fabricate it for you. So that's how you can have your clock generator here and such. So that's how a chip is made. So this is your chip. Let's say like this can be the MacBook M3. Okay, this is small for an M3, but let's just call it an M3. Or it can be an STM32F4 chip. So you can call it your own name, anyone you want. But these are the core things that you will need to do an SoC design. So this architecture, what I'm covering is basically how you can actually build in a nutshell. When you join the developer program, you'll get very conclusive learning paths on how to do this. So I would really encourage you to join the developer program. Okay, let's move on to the next page. So what is pipelining? I know you guys know this, so it will be easy to move past this because of time. So traditionally, you execute instruction in 3 main cycles: fetch, decode, execute. So you fetch the instruction, decode what it means, execute what it says. So that's how traditional CPUs or cores do. Like most 8-bit do this. But pipelining means there's a chance of executing more than one instruction at the same time. So it means that when you're fetching instruction, when decoding instruction 1, you're fetching instruction 2. So when you are executing instruction 1, you are decoding instruction 2 at the same time, fetching instruction 3. So by the time you're decoding instruction 3, instruction 1 is already done. You're executing instruction 2. and you're fetching the next instruction. So how many cycles do you take to execute this? One, two, three, four. So one, two, three, four. So the number of cycles you take is dependent on the number of instructions. If you didn't do pipelining, it means that you will take more than 4 cycles, because you will do one, two, three, finish this, then 4, 5, 6, finish this, then 7, 8, 9, finish this, 10, 11, 12. So it will take you number of instruction times the 3 cycles to execute. So 12 cycles to execute an instruction, 4 instruction rather. But with pipelining, you can only use 4, because you are kind of like every time you're decoding, you're fetching the next. You're decoding, you're fetching the next. You're decoding, you're fetching the next, executing the previous. So these are very powerful concept. Okay, it's not just in ARM, but in most CPUs nowadays, they do that. It makes it faster because it looks like kind of like multi-threading. So they can do more than one task at the same time, and it makes your CPU very fast. So when you're doing your design, that's why people use ARM architecture. It's good for this. Uh, let's talk about the AMBER quickly. AMBER, like I said, stands for Advanced Microcontroller Bus Architecture. If you focus on this diagram here, you can see, uh, and actually, if you have an STM, if I get time, I can open it. But if you have an STM and open the clocks, you will see all these peripherals. So these are your peripherals, your UART peripherals, RS-232 peripherals. There's your timer peripherals. So there's a bus that connects that to a DMA. We'll talk about DMA in a few. That bus is called APB, which is Advanced Peripheral Bus. So offering connecting low speed peripherals. Usually the peripherals are lower in speed than your core, let's say M0. It's faster than your ADCs here. So you need how to connect something to connect the two. You use AMBER. So AMBER is broken down into 3. There's AXI, there's AHP, and APB. So APB is usually for peripherals. That piece, peripheral bus. AHB is high performance bus, usually for your high speed peripherals, let's say like your RAM, your external ROM, external graphics, GPU, maybe GPIOs that are very low latency, very fast GPIOs. You use AHP to connect to it. So that is AHP. There's AXI. So for version 9, mostly AXI is used for Cortex A. It's high performance, high frequency, highly configurable IP from ARM. So this is mostly for Cortex A. So if you're developing an SoC for Cortex M, most likely you use AHP and APB. So like I said, APB is for GPU, UART, USAT, I squared C, timers. All of them are based on APB, ADCs. So peripherals that is actually faster than 8-bit, but slower than memory. Let's say your ROM should be faster, SSD. Your RAM should be faster. So you're reading your RAM, let's say at 400 megahertz. There's no way you're going to read a UART at 400 megahertz. That's too fast for it. You will get a lot of errors. So UART, let's say you're reading it at, let's say, 64 megahertz. So AHB will connect to the RAM, then APB will connect to. So AMBER protocol defines all these buses. So you don't need to come up with your own buses. No, ARM provides the AMBER protocol, whereby you can define these buses, define which peripheral goes where, and stuff like that. Okay, let's talk about NVIC and DMA. I've already handled the AMBER. So how does an 8-bit, let's say an Arduino Uno, how does it connect to ADCs? So if you have, let's say memory 1 is ADC. So for you to connect to read any ADC value, let's say a sensor, you have to go through the CPU. So the CPU has to know this is happening, then it stores in the memory or decodes it and sends it to you. But let's assume you just want to store sensor data. So you read, store, but it has to go through the CPU. But what ARM came up with is DMA, direct memory access. So what that means is that memory and memory can communicate without the CPU. So the CPU doesn't have to know. Let's say you're designing an oscilloscope or something that really has acquiring a lot of data, real-time data every microsecond, every 100 millisecond you get data. So your CPU, if you design it like this, your CPU will be so busy getting data, even data maybe that it doesn't decode, doesn't need to decode then. So this is very inefficient. So, but with DMA, you can directly store this data into your buffer or your memory. You just read and store, read and store. Then when your CPU needs it, it reads directly from memory. Number one, how advantageous this is, number one is memory is faster than peripheral. So CPU will read this data faster than reading directly from the peripheral itself. Number two, the CPU doesn't have to be occupied reading data and storing data like this. This is very bad use of the CPU time. CPU can do other things. Then later, once the data is ready, it can be notified by this memory through interrupts. That's why we have NVIC here, that our data is ready to be read. Then reads the data and do other things through interrupts too. So this makes it very fast and very powerful. I really like this feature with that ARM brings, and it's very, very powerful and efficient. Yeah, you can read more about ARM defines the DMA controller, so you don't need to design your own DMA controller. Just need to use it, know the right instructions to call to use it, enable it in interrupt mode. Different peripheral support DMA, like ADC support DMA, UART, and so on, so I2C. So you can actually do the even memory to memory. So if you have an external memory, it cannot be faster than an internal memory, so you can use DMA there. About the NVIC, NVIC stands for Nested Vectored Interrupt Controller. So interrupt, it's simple. Let's say you're playing a game on your phone and somebody calls you. So what usually happens is that the phone will suspend the game, then the call will come in. So you pick the call, talk to the guy or the lady, then hang up and continue with your game. Or you're watching a YouTube video with your phone and somebody calls you, it will pause the video. So what has happened is that we have executed an interrupt. So without interrupt, imagine your phone, like if you're watching a video and somebody calls you and he doesn't tell you. So you get like 7 missed calls, yet you were just with your phone, maybe just watching a meme or watching a comedy show. So that's not a good use of your phone. It's not helpful at all. So what happens is that there's this NVIC. What it does, it allows you to define interrupts, external interrupts, internal interrupts, and rank them. So what convention is, you can have interrupt 1, 2, all the way, let's say 3. Okay, these are the number of interrupts, A, B, up to Z. Then this is priority levels. So the higher the number, the lower the priority. So 0 is very critical priority. So, and let's say your battery is going on or is going low. That's a critical interrupt, because you can, if you call with that battery, your phone will just shut down. So it has to inform you your battery is going low so that you can plan how to charge it. But let's say there's an interrupt, like you'll receive a LinkedIn notification. That's not very critical, because number one is LinkedIn. It's not a matter of life and death. So you can schedule that as priority 4. But priority 0 is usually reserved for with an unmaskable interrupt, NMIs. So something let's say while memory fault issues, let's say while your processor was doing processing, there was some memory error. So it executes an interrupt to make the processor skip that instruction or do whatever it's supposed to do. So this is usually reserved. You can actually even set some of the interrupts as 0, so that once they happen, your program can pause and do other things, then address that issue. Then you can set others as 1, 2, and 3. So let me say this briefly. Interrupt is a very huge field. You can also research on it. NVIC, it's a very interesting field, especially for microcontrollers. But bottom line is, something that is priority 2 can preempt what is priority 3. It means that if this interrupt B and C occur at the same time, your CPU will prefer B first because it's lower priority, higher priority rather. And then after it finishes B, it now goes to C. Okay, let's say you are doing your program here. Then interrupt B, which is C, sorry, which is 3, occurs. Your main program is here, main. Your program will leave the main execution, go to the interrupt. Let's say as it was executing this, interrupt A occurred. So it will actually leave C, go to A, because A is 0, so highest priority. Finish A first, then go back to C, continue executing C, then now go back to the main program. So that is the concept of nested NVIC. So nested vector interrupt controller. So you can nest a lot of interrupts, define their priorities, say which one is more priority than the other, which is more preferred than the other. And through this, you can actually create a very versatile and robust application where If something happens, let's say your IoT for, I don't know, agricultural use, you say, okay, if there's no water at all in my garden, it means the plants will die. That is interrupt number one, priority one. So let me know. But in case the sun is, let's say, did not come up, that is number three. So let me know there was a lot of raining. I didn't get enough sunlight today, so that I know what to do because there's nothing much I can do. Maybe, or let's say there's somebody that broke into your farm. You can put that as a wrap too, because you just want to know somebody stealing your let's say maize or something. But if there was no rain, there's no water, the irrigation system malfunction. That is my most priority. So you can actually list this, and this is how the NVIC is implemented. It's its own driver that is inside the ARM core. So once you get the ARM IP, you get such. Um, so you don't need to implement your own NVIC. These are interrupt requests for peripherals, and mine is non-maskable. So these are like, let's say, memory faults, power failures, and stuff. Yeah, this is AMBA actually. So that's how powerful it is. Okay, I think the other part of my slide is just profiling some vendors. You can buy these from ST, some ST. All ST boards are based on ARM. So F4 means it's based on M4. H7. So if you see 7 is a M7, 7M7. This is M3. So G0, if you see G or 0 or F0, it's Cortex M or M0, that is for low power applications. So like you see, these are example applications of it. There's low power L also. ST has what we call L for low power, you can see. There's wireless applications, you can see. So I personally use ST because it's very simple to use, easy for new beginners. So I'll recommend this. Although you can use any other vendor. There's microchip. They have their SAM lineup, which is based on ARM. Not all microchip chips are based on ARM. So, like for example, PIC is not based on ARM. But if you see SAM is based on ARM. So you can choose which one functions from motor control all the way. If you're just buying the chip, there is NXP. They have all this lineup. So if you get a slide later, you can check it out. So by no means, I don't have a preference. Okay, I prefer ST because it's easy, but all of these are specialized. For example, NXP, I know, is very specialized in control. So you might use this. So just choose which one works for you. Yeah, I think this is not for you. Okay, I think that's it. Sorry, the time was short. I tried to finish on time. I think I did. Any questions, maybe, or back to you.
Thank you, sir. Thank you for this wonderful presentation. We have certain questions from the participants in the chat box. May I help you to read those questions, sir?
Sure, sure.
Yes, sir. First question is from myself. What are some common misconceptions or myths about ARM architecture that you would like to clarify?
Okay. I might not. So the common ones is number one is it hard? So some people, if they hear ARM architecture, they say maybe it's hard. Like I said, or it's power hungry. So of course, learning car for 32-bit might be harder than 8-bit because for starters, you're dealing with a lot of registers. But nowadays we have compilers that make it very easy for you. So we have things like HAL libraries, so the abstraction layer libraries that make it very easy. So if you go and start, if you join the developer network, you meet guys that are really developing very heavy and versatile application, but they make it in form of API. So they make it available for you. So you can call something like a convolution algorithm with just one function. You don't need to implement it. So that's one of the common misconceptions, that the learning curve is harder in ARM than other architectures. So I don't want to say it's wrong or not wrong, but nowadays with the development of compilers and advancement in that field, it's very easy to get started. Another one, integration might be. Some people say it's hard to Of course, for you to use their IP, you have to get licenses from them. So they have to allow you to use it. So that's the first thing that you need to do. It's not like AVR, which used to be just out there. You can just use it anytime. Yeah. think those are the common ones. Power and performance I've already addressed. So some people used to say, okay, ARM is good in power but not good in performance. I think that is wrong. Why? Because like I said, I'm using an M1 Max MacBook and it's the fastest thing I've ever used so far. I know there's even M3 Max, so that should be faster. So performance is way fast. It's only that companies like, let's say, Sony have not yet integrated ARM into their consoles, so our other gaming machines. So we don't really know the power of ARM in gaming, although we have seen it in iPhone 15 how ARM can game. And they in their glasses, their Vision Pro glasses using ARM. ARM renders very well when it comes to graphics. So some people argue ARM is good in power but low in performance, but it's not true. You can actually get both. You can squeeze both. So let me just wind up by saying this: in the modern world, we are in post Moore's law era, whereby Cisco is kind of like not preferred. Okay, people prefer have an option of Cisco risk. The other before 2020 or before 2018, if you just thought about performance, you thought about Cisco, Intel, and the likes. But nowadays, you have an option of ARM because ARM or risk by risk and ARM is almost the same because ARM is the one leading in the risk field. Although we have RISC-V that just came out, but it's not as versatile as ARM. Um, you have that option because ARM can also be this powerful, and guys are migrating towards it. Qualcomm is moving towards ARM for Windows, and very soon, I know one of the greatest topics we're talking about this year and the next 2 years is Windows on ARM. So once that is implemented, I know that's going to be a game changer for guys in the Windows field. And once you start using ARM for Windows, you might not go for Windows for Intel. So yeah, hope that clarifies, answers.
Yeah, sir. Thank you, sir. That was a brief answer. So let us go to the next question. By Harini Gopal. Can you discuss any recent advancements or trends in ARM architecture development?
I think I covered that when I talked about version 7, version 8, and version 9. So version 9 is built on, when you get the slides, you can go to that side. But briefly, version 9 is mostly optimized for machine learning. So things like DSP cores are added, things like FPUs are added, floating point units and stuff. Version 9 is also, there's something called trust zone for security because guys are saying, okay, if you have if the world is connected and the world of IoT, there will be some question about cybersecurity, definitely. So, how can we have secure hardware? So, ARM is focusing on that by things like error correction codes, things like what's it called? The name of this, yeah, CRCs, random. I have a Cortex M7, and it has an inbuilt RNG, hardware-based random number generator, so you can actually create an encryption on the chip itself, so that you don't need to. It's hardware-based. You don't do it with coding. So you just call the hardware and it does the generation for you. Of course, the other companies that are creating things like puffs that you can use inside, connected to an ARM-based microcontroller. So I think those are the major development is the fact that we are actually talking about Windows on ARM, which is Windows is traditionally made for CISC architecture. So if you have Windows on ARM, that's revolutionary. I saw in embedded world, ARM also announced Ethos and a chip for architecture for machine learning. I can send you the link. I will send it to Harini Gopal, I think is the one I'm talking to. Then she will send it to you guys. You can read about that advancement in ARM architecture when it comes to machine learning. Yeah.
Thank you, sir. Next question is from Sanjana Lakshmanan. What are some challenges faced by ARM architecture in terms of standardization and compatibility with existing software ecosystem?
So number one, ARM is fully standardized. That's a good thing. I just talked about even the Amber bus that allows you to connect to other IPs. So that's a good thing. Secondly is compatibility. So ARM is only compatible to systems that are compatible with RISC, so instruction sets and stuff. Although you don't need to, if you have ARM, you can design an ARM chip, then connect to another like another risk a CISC chip using protocols like SPI, I2C, as long as they support that, Like you can have a RAM that is designed by another company, let's say Marvel or Micron, not Marvel, Micron, or Samsung, then create a chip that is designed by ARM or ARM architecture, then connect the two, let them communicate through, say, PCIe or SPI. So that's one of the ways you can use to standardize the connection. So I don't think it's a challenge per se nowadays, because, like I said, there are these communication protocols and these other protocols that can call them third-party protocols that come up that are compatible with ARM and also the other parties. ARM is doing a good job. I don't work with ARM. I'm just an ARM ambassador. So, but ARM is doing a good job in standardizing most of the things so that we can actually use it, which is good. Uh, it might not. So let's say if you're designing a microcontroller, the 2-bit microcontroller, and you want to still use an 8-bit microcontroller, you might not use it directly inside the same SoC, but you can use it as a core processor. So whereby you're connecting one controller to another using a bus. So use the Amber bus to do that. So like, for example, most ADCs, the highest resolution ADCs thing is it 18 bits? If you get 18-bit ADC, you're very lucky. So traditionally is 8-bit. So like Arduino Uno ADC is 8-bit. So ARM supports an 8-bit ADC, 12-bit ADC. So what you can do is just interface the ADC with an APB bus. So that's how to make it um, um, compatible. Software based, just in a nutshell, ARM doesn't run softwares. If you're talking about Cortex A, there are some softwares that are not based on RISC architecture. A good example is softwares like Cadence, Virtuoso, or software like Altium Designer. If you're doing PCB design, it's not supported on ARM. So if you have a MacBook, you can't actually install such software. So what do you do? Or even AutoCAD, Autodesk Inventor is not supported on ARM. So what do you do in such a case? You can install a parallel virtual device, run Windows on that and install it, or Linux and install it. That's what software compatibility is a big question with ARM. So what we do is that's why ARM guys are working on Windows on ARM. So once you get Windows to comply to ARM and run on ARM, it will be easy now we will have solved that software compatibility thing. So most engineering softwares actually don't run on ARM. So for me, I have to virtualize Windows by using Parallels, or I can connect to my university's server using server connect, secure connection, then use the server. So that's one of the challenges that ARM developers face when it comes to software, especially if you're developing on Cortex A. Yeah.
Thank you, sir. Next question is from Sai Harshita. What role does ARM architecture play in development of mobile devices and IoT technologies?
So I already covered this, but I'll just say again, ARM is at the center of mobile device. All mobile devices run on ARM. There's no one that is running Intel. There's no one that's running AMD. All of them. And like you see GPUs like Mali, they are GPUs that are used in mobile devices like iPhone, Samsung, virtually all of them. Okay, I'm not sure if Huawei run ARM, but I think they do. So all of them run ARM. So without ARM, there will be no smartphones, because CISC is so power hungry. If you put Intel on your, say, Samsung or iPhone, what will happen is that within 5 minutes your battery will be out and your phone will overheat. So why? It's very powerful and very power hungry. So if it were not for ARM, it will not be a reality to have smartphones today. But thanks to ARM, we have very power efficient, powerful processors. So it's very easy to do that. So all mobile devices. So that's the role they play. They provide the hardware for mobile devices. For IoT, you have an option for either Arduino or AVR chip. You have an option for microchip PIC. But I would advise ARM, because you can run MLs on ARM. You can run complex algorithms on ARM, like convolution, moving average filters, FIR filters, IR filters, all the digital DSP algorithm you think you talk about. ARM comes with a library. I didn't talk about it, but there's something called CMISS, which is an DSP library just for ARM CPUs, and it's for all ARM CPUs. So you can use it for your IoT, so that when instead of sending data to the cloud and wasting your bandwidth, send information, process the data locally on your chip, send information to the cloud, so that you save the bandwidth, the number of bits you're sending, and also only send things that are important. So that's the role ARM plays for these devices, these two fields. And lastly, I will also say, please join the ARM developer program. Let me post the link just now so I don't forget. So what happens if you join is that let's stop sharing. If you join, it how it will help you is that you can get to see guys that really um, develop in this area. Guys are really doing huge advancement in these areas you're talking about: mobile, laptop, or Windows or desktop. So I just put the link in the chat. So join, use your corporate email. You can get to know the role that these guys are really playing in these two fields. Yeah, thank you.
Thank you, sir. We will join this link. And the next question is from Sabana Asman. How does ARM architecture contribute to the advancement of emerging technologies like artificial intelligence and machine learning?
Already covered this, I feel, but just in a nutshell. So ARM architecture provides things like DSP. So for machine learning on AI, let's say like ChatGPT, what the most important thing is number of parameters. ChatGPT has, let's say, 198 billion parameters. That's why it's very human-like. So the more the parameters, the more accurate the accuracy. So if you reduce the parameters, you reduce the accuracy. But if you increase the parameters, you increase the accuracy. So if you have 198 billion parameters, what it means that you need to do a lot of multiplication, because AI, simply put, is just matrix multiplication. It's just VMM, vector matrix multiplication. That's what AI is. So you extract an image, you convert it to a matrix of pixels. Then you have what we call weights. It's also a matrix of values, floating point values, 0 point something, negative what, you name it. You multiply them together, then you see the output. If it's not, does it look like the original matrix? If it's not, go back, adjust these weights until they're almost similar. That's what AI is. So you do back propagation, forward first, then you go back, then back propagation, then compare derivative of the matrix, see the error, we call it loss function, try to compute and such. So you see, all this is just massive mass multiplications. So it means you need a processor on architecture that is very adapted to mathematics, matrix multiplication, floating point units, precisions. The more precision, let's say 0 0.1, let's say you get 0.1234 up to 10, up to 9 rather. So if your processor is just very less precise, it will just give you 0.12, and that is not the same as 0.123. So for ARM, it has an embedded floating point unit, so which can give you 0.123456789. So it means it's very accurate that way. But if you have another one that does not have that floating point, it means it will truncate or round off your results. So you'll have a very poor loss and poor output. So it means your ML will not learn, your model will not learn, or it will overfit or underfit. Lastly, there's the DSP core, which is also optimized for ML, so you can run tiny ML. Well, most DSP cores can actually run AI models. Why? Because DSP is also mathematics. So, like convolution is what we call MAC, multiply and accumulate instructions. So that's what it does. So if you have a dedicated core for that inside your architecture and dedicated FPU inside your architecture, it's very easy for you to deploy machine learning inside it. It's very easy for you to do. You saw NVIDIA this year in GTC, they launched what we call the Blackwell chip. They also launched what we call Grace Hopper CPU. So Grace Hopper CPU is actually using ARM architecture. So the Blackwell is NVIDIA parallel, CUDA parallel architecture. But now we have this Grace Hopper that has an ARM architecture in between that connects all these Blackwell chips. And there's the one, Blackwell is one of the most powerful GPU that has ever been launched in human history. So you see, it's actually using ARM architecture because ARM is very optimized for that. Lastly, we see a world whereby we'll have machine learning LLMs running on mobile without internet connection, and that is being driven by ARM. Let me just share that link I talked about. Yeah, I have it here. I can share it with you and others. I can even share others. So you read this link, announcement from ARM. You learn more. Thank you.
Thank you, sir. I hope that's the end of the query session. Thank you for answering all the questions, sir. It was really an informative session for us.
Anytime.
Now, I would like to call Sanjana to distribute a gesture of appreciation to our resource person for the day, Mr. Fidel Makatia, sir. Kindly accept the e-memento as a token of gratitude, sir.
Wow. Thank you so much. Let me even let me take a screenshot of this so that wow. Thank you. I accept it.
Thank you, sir. And sir, with your permission, can we have a group picture?
Yeah, sure.
I request all the participants to turn on your camera, please.
Okay, we're done.
Thank you, sir, for capturing the moment. As we bring the session to a close, let's proceed with the vote of thanks.
On behalf of entire Erudite team and our student members, I extend our sincere gratitude for your enlightening presentation on unlocking career growth opportunities for student members through IEEE. Your insights into leveling IEEE resource to empower student members in their career pursuits were truly valuable. Your expertise and passion have undoubtedly enlightened inspiration and provided a roadmap for our students to navigate the path to the success within the IEEE community and beyond. Thank you for your dedication and nurturing the next generation of leader and for sharing your knowledge with us today. Once again, thank you, sir, for your enlightening presentation and for bringing an exemplary role model for us all. We look forward to apply the knowledge and insights gained by you today in a positive change in our own respective endeavors. Thank you, sir.
Thank you so much. Really appreciate, and yeah, I'll be open. I am a volunteer of IEEE, and I really, you guys are doing an amazing thing. So yeah, I'll be open to doing it next time in case you have. Of course, you reach out to me through LinkedIn, or if you have time, you can also invite me. We can continue from where we left. Really excited. Thank you so much.
Thanks to the volunteers, IEEE SJCSB thrives on teamwork and it shows in how they divide their task efficiently. Yashwant handled the speaker poster and upcoming promotions. Yashwant managed the WhatsApp content and Alex managed the Gmeet link. Sanjana took care of feedback and Emomento. Emomento managed by Ovia. Myself, Shabana, created a hosting content. Joshan spearheaded pre-event publicity on platforms like Instagram and LinkedIn. E-Momento presented by Sanjana. Screenshot documented by Hashita. Screen recording done by Hariprasad. While myself and Ritika being the host for this event. Not to forget, all the SB XCOM leads played a vital role in supporting and promoting this event. On behalf of IEEE SDC SB, we extend a heartfelt thanks to Mr. Fidel Makatia, sir, our esteemed speaker, and to our advisor, Ms. Jayarama Pratik ma'am, and counselor, Mr. Srikant Ramaswamy, sir, for the unwavering belief in us. Special thanks to all the SBXCO members for their continuous support throughout this journey.
Now, let's end the session with participants' feedback. Participants' feedback makes our forthcoming session more valuable. Now, the feedback link will be posted in the chat box. Participants are asked to kindly fill out the feedback form before leaving the session to receive your e certificates. Thank you all.